Greetings, everybody. This video will hopefully explain how to solve. This is a very common problem from rotational kinematics, where you combine Newton's second law for rotation and Newton's second law in the y direction. And let's look at this example. And qualitatively, what's going on is you have a mass of small m. It's attached to a string, and that string is then wound around a pulley, around a reel. And we're going to model the reel as a uniform solid disk. And that uniform solid disk is pivoted about an axis through its CM. And so what happens is you attach the mass to the string is wound around this reel, which is a uniform solid disk, pivoted about an axis through its CM. When the mass is released, the mass will fall and the cylinder will rotate about that axis. So the mass has fallen. So it's accelerating in the negative y direction. Newton's second law in the y direction for the falling mass. Well, the reel is rotating. So Newton's second law for rotation applied to the reel, which is a uniform solid disk. All right. Well, so first thing, uniform solid disk, pivoted about an axis through its CM. The moment of inertia is 1/2 mr squared. How do I know that? It's in the table. Okay, so that's I for the disk. So I'm going to apply Newton's second law for rotation to the disk. Then I'm going to apply Newton's second law in the y direction to the falling mass. Mask. It's a mass. I wrote mask. Let me change that. There we go. So let me go ahead and draw all the forces acting on the disk and all the forces acting on the falling mass. Well, let me do the disk, the falling mass first. Well, it's attached to a string. There's going to be the tension force. Remember, it's away from the object along the string. That's going to be T. And there's its weight. mg is pulling it down. So those are the two forces acting on the falling mass, T and mg. Now this arrow here, this is simply indicating that the falling mass is accelerating in the negative y direction. That's not a force. That's just saying, hey guys and gals, that's the acceleration. Well, that is the tangential acceleration of the disk. That's the tangential acceleration, because that's the same. The tangential acceleration of this point on the disk is the same as the acceleration of the falling mass. Okay. Now, what forces are acting on the disk? Well, there's only one. There's the string is attached to the disk, right here, right at the edge. The string is attached to the disk, and it exerts the equal but opposite tension force. That's the tension force. By Newton's third law, those tension forces are the same magnitude but opposite directions. That's the tension force on the disk. It acts, that dotted line is the lever arm. That's R. It acts at a distance of R from the axis. And clearly the angle between T and R is, because that dotted line it's a length of R. That's the lever arm. The angle between T and the lever arm clearly is 90 degrees. Sine of 90 is 1. So that tension force, that creates the torque on the disk. It causes the disk to rotate about the axis. So Newton's second law for rotation. Sum of the torques equals I times alpha. Well, the torque is TR. Remember, it's force, which is T, the lever arm, that dotted line, which is R, and sine of the angle between them. Well, clearly the angle between them is 90. So TR sine 90, or TR times 1, or TR. So that's the sum of the torques. Well, it equals I times alpha. Well, 1/2 mr squared times alpha. Well, we need to get the relationship between the angular acceleration alpha and the linear, tangential acceleration a. Well, remember, a is r times alpha. In general, tangential acceleration at is r times alpha. I've just dropped the subscript of t, but tangential acceleration in general is r times alpha, where r, that's the distance from the point on the disk to the axis, to the pivot. Well, the edge of the disk is at a distance of large r from the axis. So A is r times alpha, or alpha is a over r. So I would go ahead and replace alpha with a over r. Then 2 steps of basic algebra gives me this. Gives me that t is 1/2 m times a. Okay, now I've done Newton's second law for rotation. Now let me apply the second law to the falling mass. And my goal is I need to get an expression for the tension. I will then put that expression in right there. Well, let me apply Newton's second law to the falling mass. Well, it's mg minus t equals ma. I mean, you could write it t minus mg equals minus ma, but we don't like to do that. We typically write it as mg minus t equals ma. So mg minus t equals ma. Or t is equal to mg minus a. Then I'm going to take this expression and put it in for t. So I get m parentheses g minus a equals 1/2 big M times a. And I want to solve for a, because part A of this problem, I want the acceleration of the object. I want this tangential acceleration. Because remember, this acceleration, you see I've taken that dotted arrow indicating the acceleration, I've moved it right here. You can see it is the tangential acceleration of this point on the edge of the disk. And so I want to, in part A, I want to solve for that acceleration. So when I take, I get apply Newton's second law to the falling mass. I get mg minus t equals ma. Rearrange this to get an expression for t. Take that expression for t, put it into equation 1. Then once I get that, solve for a. And I get a is equal to, I get this expression for a. Plug in the numbers and you get 7.57 meters per second squared. Then part B of the problem, I want the tension in the string. Well, I can get that once I know A. I can use this equation to get the tension, get 11.4 newtons. Now I want the part C, I want the speed with which the object hits the floor. Well, I can use kinematic equation 3 to get VF. And remember, I'm using kinematic equation 3 with VI equal to 0 and YI equal to 0. And that gives me VF squared equals 2AYF. Remember, this is not, the acceleration is not G because it's not a free fall problem. Because the mass is attached to the string, which is then wound around the pulley. It's not a free fall problem. The acceleration is in the negative Y direction, but it's A, it's not G, because it's not a free fall problem. And so you get kinematic equation 3 with VI equals 0, YI equals to 0. Gives you VF squared equals 2AYF, or VF equals the square root of that. And you get the 9.53 meters per second. But that's it. Remember, you want to apply Newton's second law for rotation to the disk, the uniform disk, which is the real. You get an expression for t. Then you apply Newton's second law to the falling mass, and you obtain an equation for t, which you put into, in this case, an equation 1, and solve for a. Now there's an easier approach, a little bit easier. There's a conservation of energy approach to this type of problem. We'll look at that next. But that's, again, Newton's second law for rotation and Newton's second law in the y direction applied to the falling mass. Let me go ahead and save this video and get it posted.